the conference, and that's my second time. My talk is about organic inorganic nanocomposite membranes for PEM, which is proton exchange membrane fuel cells. I am going first to speak about So first, why fuel cell? Fuel cell is because of environmental concerns, global warming, climate change, depletion of fossil fuels, and also about hydrogen economy, which is for energy security and the energy transition, and also the government's policies, because everybody is looking for the hydrogen. And it's mainly hydrogen fuel cell. What is fuel cell? Fuel cell is an electrochemical device which converts chemical energy to electrical energy. Fuel cell differ than a battery in that fuel are continuously supplied and the products are continuously removed. So fuel cell is working as long as there is fuel, and especially for the vehicular application. So there is different type of fuel cell. There is at the bottom the two last, they are high temperature fuel cell. The three at the top, they are low temperature fuel cell. So my talk is focused on PEM fuel cell, which is proton exchange membrane fuel cell. So what the advantages of low temperature fuel cell? They are small size, much lower operating temperature, and they have variety of application, low power devices, vehicular and stationary applications. So this one is Ballard 1 kilowatt PEM. That's stationary, and the most advantage of the use of fuel cells, low temperature fuel cells, especially PEM, it's vehicular application. This one, they are the first models in 2000, around 2000, 2005. And this one is the latest models. And this year, BMW joined all the companies, because all of them, they have fuel cell vehicular vehicles, except BMW. At the beginning, they opt for hydrogen, but to use it directly in internal combustion engines. And now they changed their mind, and they are also joining the fuel cell vehicles, and which are they're completely different than the Tesla, because the Tesla, they are using lithium-ion batteries, but this one, it's a fuel cell. So as you saw, the cars, they are 100% the same as internal combustion engine. The only difference, they are very clean. So we can see here, unfortunately I don't have the pointer, but you can see the principle of fuel cell. So we have the anode and we have the cathode. We have hydrogen oxidation at the anode side and oxygen reduction at the cathode side. And we generate electricity. And the only byproduct is water and heat. So you have electricity, water and heat. And that's why everybody is looking for fuel cell, and that's very important. So this one is in details. So we can see hydrogen fuel cell, and this one is methanol fuel cell. DMFC is direct methanol fuel cell. So that's the oxidation. Here is the reduction, and all the time we get electricity. So what's happened in the oxidation? In the oxidation, we have protons and electrons. The electrons we capture in the electrical circuits, external electrical circuits, and the protons, they must go through the membrane. So to the cathode side, at the cathode, there is oxygen reduction, and then we produce water. So the heart of fuel cell is the membrane. So these protons, they must move from the anode to the cathode. This one is okay. Yeah, it's fine. Yeah. So here we can see clearly, that's as I said, the most important is the protons must move through the membrane from the anode to the cathode. And for hydrogen, it's fine. If we have methanol, as we can see here, if we are using methanol, so we have also the methanol going to the membrane, and that's a problem. So all my research, here we can see the reactions. So that's hydrogen fuel cell. This one it's methanol fuel cell. You see the difference is the product. In hydrogen fuel cell, we get only electricity, water, and heat. That's excellent. For DMFC, it's different. There is CO2. There is also methanol. There is methanol going to the membrane, which is not convenient, which I am going to probably speak about it. But that's the principle. Theoretically, both of them, they are excellent. Both of them has advantages and disadvantages. This one, it's a single cell. It's look easy, but if we go to the details, each part is very difficult. So you can see here is the end plate. That's the flow fields. In this case, it's a serpentine. We have here the MEA, which is the heart. So the MEA is a membrane electrode assembly. So we have a membrane, and in each side of the membrane, from the anode side and the cathode side, there is the catalyst layer. Behind this, there is a GDL, which is the gas diffusion layer. So that's the gas when it's come in the serpentine to reach the electrode. They must have a gas diffusion layer, which is carbon paper or carbon cloth, to diffuse the fuel. So that's another side. This one I added because it's more clear. This one is very important. It's gold plated. So that's for current collector. So the people that are working in fuel cells, so each one take a part. The first slide, it's engineering. So there is laboratories only specialized in the engineering. They don't look for other stuff. In my case, I am looking for the membrane. Now we are moving to the catalyst. Some people, they only look for the catalyst, which is the electrocatalyst at the anode. Some of them, they look for anode and cathode. Some of them, they look only for the anode to reduce the loading. The other ones, they look for the cathode, and especially OR reaction, oxygen reduction reaction, which they call it methanol tolerance. So if there is crossover, that methanol will not react. Let's speak about methanol crossover. In this reaction, so that's methanol, so you have protons and electrons. So the electrons we capture in the external circuits, the protons will travel through the membrane, but also we have methanol going through. The problem with this, at the anode we have platinum, which is very good for methanol oxidation. The problem we have also platinum in the cathode. So if methanol crosses the membrane, so it will be a competition between oxygen reduction and methanol oxidation at the cathode side, and the efficiency of the cell will drop. So that's why we need to do some things to block this methanol to go through. So as I said, I am in this presentation focusing on membranes. So that's some of the developments of the membranes. But the state of the art commercial materials is Nafion. There is Nafion series, there is also from other companies, but the most important is Nafion. All the prototype I know, they are all with Nafion membrane. That's Nafion. Nafion is from DuPont. So the membrane is good, we are going to see. In our case, we are also now studying sulfonates polyether ketone, and we mix it with different inorganic fillers. And also we did chitosan membrane, and also we are developing other type of membranes. but mainly we are not looking for polymers. This one, it's an exception. I am looking for it because my partner or collaborator is a polymer scientist. So he knows exactly how to put sulfonate groups in the peak. So the advantages of Nafion, it's very good. High proton conductivity up to 90 degrees, and the reason is because of water. So the membrane must be well hydrated. High chemical stability and high mechanical stability. The disadvantage of Nafion is high cost, high methanol permeability, and losing conductivity about 100 degrees. And the reason is because of water. So as soon as it's dry, it loses the conductivity, and you have no fuel cell at all. So how we cover some of the disadvantage of Nafion. So the most important one is to add inorganic materials. So like in this case, we use zirconia, we use sulfated zirconia, we use silica, palladium, titanium, zeolite, that's a clay, and zirconium phosphate. If we take the order in our experience, the best one is zirconium phosphate, which I am going to speak later about it. I'm supposed to speak about all the ones except the ones in italic because we didn't publish yet about them, but my presentation is supposed to go in details about this, the XRD, FTIR, TGA, whatever we did. But I changed my mind yesterday. I said, no, this one is conventional. So it's normal, you prepare the nanomaterials and you disperse them in the polymer. So two things you need to look at. The materials must be less than 10 nanometers and the loading must be around 5%. These two conditions can satisfy. The reason why it's nano, because nano it's high surface area, but the nice things about nano, it's a very good dispersion in the polymer. So if you have nanomaterials, you can disperse them easily without agglomeration. The 5% loading, it's because of the agglomeration, because if it's go to 10%, you can see agglomeration in the polymer, and that's not good. So the presentation will stop here, but I am going to give you some of the publications and different materials we used. So it's mainly in this project, Dr. Segwade, she did her PhD in the field from the end of 2015, 2019. And I think she did 12 publications in her PhD. So she combined too many things together, as long as it's nanoparticles. And each one has the advantage and disadvantage. Now, we did most of the work. It's already done. But one of the problems with all the developers of membranes, they did it alone. Let's say, Nafion zirconium phosphate. He prepared the membrane, zirconium phosphate, then mix it with the membrane, making nanocomposite material, then test it, go through all the tests, include fuel cell test, and they compare it to pristine Nafion, or taking Nafion 117, which is a reference. And that's it. So now what I am hoping to do, I am hoping to go to postdoc, which he or she will look after a systematic study of all the organic, inorganic materials. What it means that we are going to see what is the impact of the shape, nanotubes, nanorods, nanospheres, nano whatever. And the second thing is the size. What is the optimal size? So we will study thermal analysis or thermal property, mechanical property, fuel cell property. So each one we systematically, all of them together, with the same technique, with the same experimental setup. Then we will detect scientifically what is the difference and why. So I'm hoping next year to regulate the postdoc. So I welcome any applications from this audience. So I want to speak about something which is different. It's a membrane we didn't publish about it, but we are going to continue because I like the type of the membrane, it's new. So the two main importance for fuel cell is proton conductivity. So this one, now we have this equipment from grid light, which we can measure the proton conductivity at high temperature, up to 200 degrees, and reduce relative humidity. We can start from 0 to 100% humidity. The less humidity is the better. The highest temperature is the better. Because the catalysts, they work at high temperature very nice. Let's say methanol oxidation. Methanol oxidation is very sluggish reaction. But with Nafion, with pristine Nafion, it's 90 degrees. That's the maximum you can go. But if you work at 120 or 140, mostly 140 degrees. So the catalyst is working much better than 90 degrees. That's one. For the electrode also, it's very nice to work at high temperature, because if you work, let's say, 140 degrees, you can use a reformized hydrogen. What it means, a reformized hydrogen? You take methanol, you do reforming to hydrogen. The problem with the reforming, you get CO. You cannot remove the CO. So you need a CO tolerance catalyst, because platinum as it is not CO tolerance. If you inject hydrogen with CO, CO will poison the catalyst. So, but at 140 degrees, you don't worry about CO. This one is very important. As I said, we want to reduce the methanol, or we need to know how much methanol is going to the membrane. There is different methods how to measure methanol permeability. We are using the last one, the diffusion cell. Because I am from the Department of Chemical Engineering, we know this method much better than the others. So we use zirconium phosphate, as I said, it's the best. The reason of zirconium phosphate is the best is surface conductor. So surface conductor, previously these people, they use zirconium phosphate, or they synthesize zirconium phosphate, but at a micro scale. So if you have zirconium phosphate at a nano scale, surface conductor, so itself is proton conductor. And that's what we use it. So to make zirconium phosphate, we start from zirconium oxide. This one, it's one of the ways to prepare it. So that's our method. And we compare it with the commercial ones. The presentation is old. So this one is to see what is the size of zirconium phosphate. It was around 12 to 14. Now it's much less. With the PhD project, it's much less than, I think it's around 1 nanometer, the size. Zirconium phosphate, that's also zirconium oxide. Zirconium phosphate, it's around 30 to 40. And the other one is the same, which is very good. Because, as I said, the previous people, they prepared zirconium phosphate, it was micron. And we are in nano. So it's this one to confirm that we have zirconium phosphate. So that's what we did in this. So we prepared zirconium phosphate, nanoparticles, but also we use a flexible ceramic materials. This material, that's a ceramic inner fibers. This one is from Degussa. Also, that's another materials, also from them, the same principles. So they call it a flexible ceramic. And what we did, so we check, that's the characteristic of the clay filter as it is, without any filler. So we can see the permeability, which is very important at the end of the membrane. And that's the solubility of the material or the stability of the material. That's the matrix. What we did, we impregnated with zirconophosphate. First, we took the material, the bad one, and we impregnate zirconophosphate. Here we see methanol permeability. That's the reference, Nafion 117. Nafion 117 is 175 microns. This material, it's less. So you can see here, it's 100 micron. Okay, this one is 200. This one is not good. The two ones, that's the good ones. It's not me. في slow.
الجيل الاخر من هيك
Sorry. As I said, Nafion 117 is the reference member, and it's state of the art. In all the cars they are using Ballard, they are using only Nafion. So we can see here Nafion is the second one. That's the reference. So anything is under it, it's better. So we can see Z100G and 240G, they are much better. So here, all the membranes, we can see the characterization. As I said, the thickness is very important because the thicker the membrane is, the less methanol going through, but less conductivity. So you need to balance between conductivity and methanol permeability. And to understand an indication about the performance in fuel cell, in a real fuel cell, you can see the selectivity factor, which is conductivity divided permeability. So that's the reference, which is Nafion 117 is 4,5. So anything above this, it's better. So we can see this one is better. It's supposed to perform better than Nafion 117, the reference. So the second type of membrane we take the flexible ceramic material and we impregnate with Nafion solution. So you can see here, this one Z200 and this one is 240 Nafion. This one is better than the other one because the loading of Nafion is much higher. And I assume it's because of the pores. Because I think this number is the pore size. So if we see the permeability in this case with Nafion, it's the ceramic Nafion solution, it's much better than the reference for methanol permeability. And this membrane, It's very important because the conductivity also. You can see here. Okay, this one I don't like, but these two, I'm talking the conductivity. So the conductivity you can see here, okay, this one and this one. So this one, the conductivity is half, the permeability is better, and there is the third advantage of this material over this one, because this one it's a film, Nafion film. So all of it is Nafion, and Nafion is very expensive. But this one, it's only a part, plus minus 10%, 20%, I don't know, I never calculated, but it's only a part because we take the ceramic material and we impregnate. So if we look for the same picture, you see, that's the material, but the one they give this dark color is the Nafion. So you can see how much you are saving on the cost. Plus the performance, they are nearly the same. And methanol permeability is much better. So this one, what we did, we took the Nafion solution and we make a membrane. And we mix it with the nanomaterials. So that's what, this one also is the same, is zirconium phosphate. So we can see here it's very important the loading. As I said, 5% is the optimum, because the more you add, you get agglomeration and you don't have a good mechanical stable membrane. And one of the problems of Nafion as a film is the lifespan of the membrane. The membrane will deteriorate. I'm not sure about the regulation now, but it was 40,000 hours. So it will start to deteriorate. So if you add more inorganic materials to the membrane, so your lifespan of the membrane is reduced. So all the time, as I am saying, it's a balance. So you need to understand your materials, how they behave. And you take the balance, and any disadvantage you try to overcome somehow. This one, it's recourse Nafion zirconium oxide. We see the methanol permeability. So in this case, all of them, they are worse than Nafion, because Nafion is the lowest. But doesn't mean that it's bad, because all the time there is something else we are going to win on it. This one is very important because Nafion is proton conductor, zirconium phosphate is proton conductor. So when we put them together, we increase the conductivity of Nafion. So the nanocomposite materials, it's better than pristine film. So in this case, you can see we reduce it to 12 nanometers. Especially zirconium phosphate, the higher surface area, because it's surface conductor, the higher surface area is the better. And the smaller the size is the highest surface area. This one, it's very important because we are using the film, Nafion 117, which is the film. And we impregnated with zirconium phosphate with ion exchange in the film, not the recourse, because in the previous ones we prepare the powder and we introduce it to the polymer. This one we take the polymer and we impregnate it by ion exchange. And this one to confirm that we have zirconium phosphate in the membrane, in the film. It's not moving. Okay. So this one is also to confirm that we have, with the ion exchange method, we have still nanomaterials, nanoparticles of zirconium phosphate. Here it's it's much better methanol permeability because it's the one. So here we can see that's the reference 4,5. So these two members, they are better than the reference. So here we did the composite twice. First we take the inorganic material, the matrix, we put naphthalene, and then the naphthalene inside we impregnate it via ion exchange with zirconophosphate. Here is DMFC performance. So all the time I am saying the selectivity is better than naphthalene. The selectivity is better than naphthalene. So it means that it's supposed to perform better than naphthalene in a real fuel cell, which is not the case. Because one of the things about the fuel cell, so that's the membrane, and we have here the catalyst layer, and we have the GDL, the gas diffusion layer. So here it's very complicated to make the electrode. So the technology was developed specific to naphthalene. So you need to have, that's the optimal setup at the electrode. So what it means that this one is the anode, the reaction. So you are going to create this one, the black one, they are the catalyst, platinum. So what's happened? One hydrogen rich, so it will produce protons and electrons. So if this one, that's the platinum. So hydrogen will enrich it, there is protons and electrons. The electrons must go this way to the external circuit, and the protons must go to the membrane. So you need to have electron path and a proton conductive path. So at the beginning they struggle, then what they decide to introduce, because platinum is on carbon. So you have electron path, but you don't have the proton conductive path. Because if this chain will break, so your protons will stop. So you need a carrier, and naphthalene is one of them. So they mix naphthalene solution in the electrode. So it's not easy, but whatever they develop it for naphthalene. So any material, you will find that is not performing as it's supposed. You need also to develop or to look for the electrode. Let's say here is the cell performance with commercial stuff, E-Tech carbon cloth. This one is 2 milligrams per loading. We buy it as it is, and we try it, and we can see you see zero. That's naphthalene, pure naphthalene, 0%. Which one? This one? Yeah. So it's the lowest. So what I am saying, that's when you develop new materials, it looks nice, it's supposed to perform very good, but you need to continue in the development. And that's what, so let's say this one is the GDL. We use different type of GDLs because we want to, because our objective is not to develop the material, we want to develop a working fuel cell. So we need also to look for the other parts of fuel cell, which is not easy. And especially when you develop something which is not conventional. So let's say also the PTFE in the electrode is very important. So in our case, we look for the membrane, and now we are looking for the catalyst. So it's not 100% our duty to look for fuel cell performance, because there is, as I said, people they are specialized. In the past, when I was busy with my PhD in fuel cell, Los Alamos was the reference. They never develop a membrane, they never develop a catalyst, they never develop a GDL, they never develop, but what they develop, how to combine them. Let's say the MEA, how you make the MEA. The MEA is the membrane. You have the other side, the anode, which is platinum. On the other side is a cathode. And the GDL, which is carbon paper or carbon cloth. And then what they did, the electrode they prepare is the optimal one they showed you. They mix what they prepare in ink, including Nafion solution. It's very specific way how to prepare it. Then they spray it on the GDL. They try first on the membrane, it's very difficult. So they put it on the GDL. Then they call it hot pressing. They heat it to 180 degrees, which is the gas transition of Nafion. So Nafion in the membrane will be soft. Nafion inside the electrode will be soft. And then they press it together. And they form the MEA. So when you go and you buy in MEA, and they don't tell you how they make it. You see, this one is, we try to see the impact of catalyst loading on the cell. This one, we took pictures of the cell, of the electrode. Here we compare with Nafion, and our performance is less. This one is the reference, and our performance is less. And there is many reasons for that. But the most important one is this one. You see, this one is the MEA I am talking about. You can see that's all that, it's layer after the layer after the layer. And here there is a big problem. We have delamination. If you have delamination, you don't have a good MEA. And the reason, because here everything what we did was developed for Nafion. But here we are using something else. That's the main material, which is not going to be to perform as for Nafion. So any materials you develop, you modify it, it's better. But when you want to adopt it for the application, it's another story. Thank you. Oh, sorry. Yeah. Okay. I want to do another presentation which is different. It's not a presentation. In January next year, we are going to start an institute. The institute is Catalysis and Energy Solutions. I am going to give you a brief about what we are going to do. We are busy with it, but differently. Now we join all our efforts and we form this. So there is 5 people we are involved, and we are going to look for more people. So we are going to give you the topics or the thematics we have in this new institute. So the name of the institute is the Institute for Catalysis and Energy Solutions, ICAS. So the reason we focus on this too, because the two principal focus area is catalysis, because catalysis in chemical engineering, we know it's 90% of processes they are catalysis or catalytic processes. And energy solution, everybody know about energy, everybody is talking about energy. It's security of supply, energy access, and it must be clean and affordable. So that's the focus areas. So we have the catalysis side and the energy side. From the catalyst side, we have heterogeneous catalyst for clean energy production, advanced catalytic materials, catalytic reaction engineering, modeling, and process synthesis. From the energy side, we have biomass, waste, and CO2 valorization. We have energy conversion devices, that's fuel cell, and we have advanced energy materials. So that's what we are looking for each topic. So in the catalysis, we are looking for clean energy production, synthesis gas generation. As you can see, syngas is You can break it to anything. You can follow. If you have syngas, you have everything, whatever you want. So we have CO2 conversion into fuels and chemicals, green olefins conversion into liquid fuels, direct methane conversion, gas and liquid cleanup, hydrogen production, because you can see here hydrogen. But also hydrogen, you can get it from methanol, you can get it from DME, which is dimethyl ether. We can get it from Fischer-Tropsch, but they say that we cannot go through this route and then you go back to hydrogen, which is crazy. So, because Fischer-Tropsch is the most important reaction in the gas conversion. And in South Africa, we have Sasol, which is a world leader in that. So advanced catalytic materials, we look for photocatalytic materials, electrocatalytic materials for fuel cell, mainly, flexible sensors, and advanced catalytic preparation materials. This one is Professor Liu. The previous one is Professor Liao. They are Chinese. We are collaborating very much with China. We have even labs in China. But the Chinese government has very good programs. The catalytic reaction engineering, it's mainly about process synthesis, simulation, and intensification. This one also is very important. That's Professor Mate. Lithium-ion battery, metal oxygen batteries, advanced hydrogen electrolysis, that's me. I am looking for PEM electrolysis, and I am going to look for PEM electrolysis and solid oxide electrolysis. Hydrogen storage, also it's me. With other partners also they are doing some things. In my case, I'm developing composite materials. It's a LEAP-RE project. I am working with Professor Mostafa Talfawi from INSTA Bretagne in France. So we are preparing composite materials for liquid hydrogen storage. Energy conversion, it's all what I did and we still doing. Most of them, they are fuel cell. The only new things we are going to look is solid oxide fuel cell, because solid oxide fuel cell is for power generation. It's high temperature, so any fuel can go through. Like people, they say that natural gas don't have a future. As it is, conventional natural gas and the conventional use of natural gas, it will stay until 2060. But after 2060, natural gas will be used in solid oxide fuel cell. So natural gas will stay and forever. This one is Professor Patel. He is looking for biomass to energy, mainly gasification, pyrolysis. But also he's doing other stuff like hydrothermal carbonation. All of us together, we are doing biodiesel. And we did biodiesel before, and also CO2 conversion. Thank you. Okay, so that's the conclusion from our institute. It's a futuristic one. So all what they are doing will stay well beyond 2050. Thank you.
Thank you very much for your talk, Professor Touhami. We'll now leave the floor for more questions, if there are any. So.
Thank you. Okay, I'm Professor Sihan Barama at the University West of Algeria. Can I ask you my questions in French? No problem. Ok. Alors, je voudrais savoir, vous avez parlé de la pile à combustible, la pile hydrogène. Je voudrais savoir, est-ce que cette pile a une solution à long terme? Sachant que, par exemple, parallèlement, on peut donner des exemples, la pile alcaline, elle est recyclable. Le pot catalytique est recyclable. Donc, le pot catalytique, c'est Catalytic Converter of Vehicle. Mais la pile à combustible, c'est un prototype complexe et qui a une durée de vie. Et donc, l'accumulation pourra constituer dans quelques années une nouvelle source de pollution. Donc moi, je voudrais savoir si elle a vraiment de l'avenir. Ça, c'est ma première question. Ma deuxième question concerne votre deuxième short communication. Vous avez montré le bioéthanol comme fuel, c'est ça? Le bioéthanol, en réalité, tout le processus de fermentation et tout, le bioéthanol a des additifs. Hein, à la fin du processus, il n'est pas pur, l'éthanol. Il y a des additifs, c'est pour ça qu'on dit bioéthanol. Donc, ces additifs engendrent, lors de la combustion, engendrent des impuretés insouhaitables, indésirables. Donc, pensez-vous aussi que le bioéthanol a un futur sûr, quoi, enfin, un futur... voilà, c'est tout.
Ok, merci. Bon, هذا بالعربية. Ce qui concerne l'hydrogène, les piles à combustible pour le futur. أنا أعطيت l'exemple تاع BMW. BMW حتى ريسامون ما كانوش يامنوا بالفيول سيل. Actuellement حتى هما عندهم BMW X5 فيول سيل. ما فهمتش لا كيستيون الاخر. لا واش قلت لي؟ نو قبلها على الفيول سيل لي بيلا كومبوستيبل قلتي باللي ينسوس ريسيكلابل ولا؟ Non, il n'est pas complexe puisque the technology is well developed. You see, fuel cell it's used in the 60s. All the space shuttles they have fuel cell, so the technology is very well developed. The problem with the fuel cell or le problème avec les piles à combustible, c'est les compagnies pétrolières. Oui, l'hydrogène, tout ce qui concerne l'hydrogène, c'est les compagnies pétrolières. C'est ExxonMobil, c'est Shell, c'est Total, c'est BP. Oui.
En Nouvelle-Zélande, il n'y a plus d'automobiles. La Nouvelle-Zélande, c'est que des automobiles à pile à combustible. Et tout le monde le sait. Depuis, je crois, 2015-2016.
Non, le problème avec le recyclage.
Le recyclage, il y a un autre problème. La pile à combustible, la voiture, quand elle est équipée d'une pile à combustible, elle évacue quelque chose quand même. Parce que la pile à combustible, elle remplace le fuel et le convertisseur, catalytic converter. Elle remplace tout le prototype. Donc si elle remplace, il y a une émission, tout le monde le sait, c'est H2O. Elle émet de la vapeur H2O. Or, la vapeur H2O, c'est le greenhouse, c'est l'effet de serre number one. Tout le monde pense que c'est le CO2. No, it's false, c'est faux. Number one, c'est H2O vapeur. Parce que H2O vapeur, quand il va partir en atmosphère, il va jouer le rôle d'oxydant, il va favoriser les réactions photochimiques, et plus il y a du carbone, on peut avoir beaucoup de vapeur d'eau dans l'atmosphère, et on va favoriser le CO2. S'il y a moins de vapeur d'eau, le CO2, la couche d'ozone ne va pas s'étendre dans quelques années, ne va pas avancer. C'est est-ce que vous avez compris?
Oui.
Dans la nature, la vapeur d'eau provient de l'évaporation des océans, des lacs. Mais si on rajoute encore une production de H2O, je ne suis pas en train de démolir le prototype pile à combustible, mais il n'y a pas que des avantages. Ça, il faut...
Bien sûr. Bon, premièrement, c'est la première fois que je نسمع هذا. Merci, ماذا بيا تعطيني plus d'informations. ما كنتش على بالي أنا باللي. سي فور بوسيبل على بالهم باللي كاين هذا بروبليم وما حبيش يهضروا. واش على بالي لو كان نشوف لا بريزونطاسيون الماء كي يخرج كيما في الاخر في سبيس شاتل على ليبوك واش يديروا؟ يحكموا امباتي من الماء يشربوها بور درينكينغ لا كونسوماسيون، امباتي منها يديروا لها الكتروليسيس. جوستومون لا بليبار راهم يديفلوبي ماشي لا كومبوستيبل مي كومباين. Elle produit l'électricité والماء هذاك الماء ينباتي منه يحكموها يديروا لها الالكتروليسيس بور لا برودكسيون دو ليدروجين ويقعد هذاك الماء يدور. فهمتي؟ مي سي لا بروميير فوا اللي نسمع باللي لا فابور تاع لو سي حاجه جرين هاوس افكت.
On l'a utilisé dans les dirigeables pendant la Deuxième Guerre mondiale. L'hydrogène, c'est pas quelque chose de nouveau. C'est quelque chose qui date depuis des
على بالي كيما البروبليم تاع
un clean fuel que convoitise.
Non, 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 rien n'est innocent. Le problème avec les batteries, les electrical cars batteries, Tesla, le problème c'est le lithium. Il n'y a aucune technologie de renouvelable énergie يقول لك باللي zéro emission. ما كانش منها. باسكو هي لا كيما الفيول سيل. لو برانسيب تاعها زيرو ايميشن. مي باش تلحق الماتيريال تخدم الماتيريال كامل باش دير لي كومبوزون شحال كونسوميت المينيي منين جبتو كيفاش جبتو الاخر. بون كيما الاخر لاندستري بيترولي بكري كان يقول لك فروم ذا ويل تو ذا ويل من البير الاخر الروضه بون بالعربيه. ومن بعد قال لك نو هذه ايضا غلطه ما نقدروش نبداو من الوال نبداو من قبل الوال. ومن بعد ولاو خرجوا البرانسيب من المهدي الى اللحد من نهار تخلق حتى تموت هكذاك باش دير لايف سايكل الحقيقي. اوكي سكي كونسير لو بايو انا واش قلت لك كي قلت لك بايو ديزل ولا البايو ايتانول قلت لك خدمنا باسكو انا هو مفافوريجيس باسكو بروفيسور يا sometimes back. Professeur Patel, qu'est-ce qu'il fait? Il يحكم la biomasse, يدير لها gasification pour la production تاع السينغاز. Une fois عندك السينغاز tu peux faire أي حاجة حبيتها. بيان سبيسيالمون لا بيتروشيمي بكري دلوك اللي يسميها لا غازوشيمي. باسكو لا غازوشيمي ديرها من السينغاز. وسينغاز تجيبو من بايوماس على هذه يعتبروها رينوبل انرجي كي يقول لك دلوك اكتويلمون كي يقول لك بايو ايتانول وبايو ميتانول. C'est pas la conventionnelle, c'est pas la fermentation. C'est le gasification ou la pyrolysis. Ok, madame.
Bon, bonjour à tous, donc, associate professor in chemistry at Farhat Abbas University, and my name is Jennifer Boumer. So my field is not the PEM fuel cell application. I never work on this field, but I work in my thesis on the elaboration of thermoelectric material, which the principle is to convert the thermal energy on electricity. So when during your presentation, which is very good and very informative, I saw that we can I have two questions. The problem of thermoelectric material, we have elaborated in bulk material and in layer pink material. And in pink material, we have problem of the stability and the potential of the efficiency in à long terme.
Oui, oui, en français on a là.
Non, parce qu'il y a.
It's okay, he understands French.
Français, d'accord. Donc, ma question, en fait, the use of this thermoelectric it's the same, le même principe, the same objective that we can translate, we can produce the electricity like the PEM's fuel. We can use the thermoelectric as semiconductor in the for the tuyau d'échappement. In English is we say exhaust pipe. Thank you. So should I it's just an idea for the inorganic nanocomposite membrane? We can elaborate so the objective is to translate this or use you have used a ceramic material. We can use, for example, the same process with the same. We can extend the idea, but we can use the thermoelectric material and combine with inorganic, for example, nanocomposite, in order to produce thermoelectric efficient material. And we can, the second question is that we use this thermoelectric, combine this thermoelectric material with this material for this application PEM fuel. Because they have, en fait, ils ont un point commun, c'est par rapport à la production de l'électricité. Et voilà, sachant que c'est pas mon côté pile, c'est pas. Voilà, merci.
J'ai un collègue, Professor Rao. He is a mechanical engineering. He is working in this field. I can introduce you to him.
Yes, yes.
Yeah, he is preparing. His studies the thermal analysis, and I don't know how nanofluids. He's using also nanofluids, and at the end there is fuel cell, and that's why he's speaking with me on this regard. But we never work in collaboration. But I can introduce you to him. If both of you can bring something to fuel cell, yes, you are more than welcome.
I saw that in the second presentation you have proposed advanced material energy. You can propose.
Yes, that's Professor Mate.
Suggested that thermoelectric material is a big problem, and more people that don't. I'm not convinced.
Yeah. One of the things we have chemistry departments, we have physics departments, mechanical engineering, electrical engineering, chemical engineering. Yeah, and plus the institutes. All of them they are in energy and materials. All of them we are developing materials for energy. So you can fit very nice.
Yeah, I'll ask one question, so just be quick, and then we go for lunch, okay? Very technical one. When you spoke about the membranes, specific membranes that would actually stop the movement of methanol from one chamber to the other, or the fuel cell, did you get to study the polarity of the surface of the membrane that could have an effect on repelling methanol molecules from approaching the membrane in the first place? I don't know.
Which principle?
The polarity of the membrane.
What do you mean polarity?
When you spoke about the charge on the surface of the membrane, so if the charge is positive, for example, that could have actually a potential to repel methanol molecules from the surface of the membrane, and perhaps.
Yeah, for methanol permeability, I didn't say it, but I showed that we are using palladium. Palladium is the best. Palladium is, you can put a layer of palladium and it can stop methanol from going through without affecting the performance of the membrane.
Okay, so I think it's about time that I go for lunch. The lunch is again, it's upstairs in the first floor. We'll hope to resume in about an hour time, so say like 2:15. So it's 2:15. We'll resume here, and then we'll talk about that later. Okay, so we have an unscheduled speaker for 10 minutes who wants to give a quick presentation. We will try and present her now, and hopefully there won't be any questions to ask after that because we are really in a rush, okay? So, where is the... Okay.
هذا تحتاجه.
Merci.
Yeah,
it was great. Thank you.
Professor Dr. Sahar from Egypt, at the University of Mansour University.
Cool.
Before my announcement, I would like to introduce myself. My name is Mustafa. I'm a professor of Inorganic Chemistry and Biochemistry Department in Faculty of Science, Mansoura University, Egypt.
Sorry, please, mic. Thank you.
Much better. Okay. Okay.
Thank you.
Very quick CV. Okay. A quick CV. I got my bachelor degree in 1985, excellent with honor, and my master degree in 1989, and my PhD from Imperial College London in 1993. Visiting professor in Ioannina University, Greece, McGill University, Canada, Imperial College London, and also I got some training in Japan, in Hokkaido University. Actually, I'm interested in my research is interesting in preparation of inorganic complexes and with catalysis, environmental, and many other applications. Alhamdulillah, my H index is 27. I have 98 publications, 4 chapters in different 4 books, and actually all more than 50 plenary lectures in different countries. And my research is appreciated from Mansoura University in Egypt, Azhar University, from cofinder in South Africa, in Cape Town, and in Spain, in Barcelona, also in India, Pakistan, and finally from Algeria, from Steve. The point which I would like to speak with you about it is about how we can be members in the International Bank, the Islamic International Bank, which is in Kingdom of Saudi Arabia, but it is organized by the COMSTEC from Islamabad, Pakistan. 2 weeks ago, I was in Pakistan, and I met the Prime Minister and the Minister of Higher Education, also the coordinator of the COMSTEC. And they were astonished that Egypt and Algeria, they are not members in the COMSTEC and the International Islamic Bank. And we start our steps, how we can be members. We need 2 points, academy and society. And that's why I'm starting already in Egypt by organizing an international workshop about the environment and how we can treat pollution. Firstly, which is supported by the Chemistry Fellowship Society, which is a member in the Arab Chemistry Society as well. And as we have a cooperation with Farhat Abbas University here in Algeria, 5 years ago, we start to also again, I was contact my colleagues in Steve, and also they let me contact Professor Wahab here in Algiers, and inshallah after this talk, I will go away to meet him and arrange to have some cooperation between the academy and the society. And I think after this step, we will have the chance to be members in the COMSTEC and the International Islamic Bank. Why we are looking for that? Actually, the COMSTEC is supporting many activities, which is firstly, every year, 700 grants for PhD and master degree. Secondly, supporting conferences, financial support, also supporting participants, maybe by flight tickets, visa, pocket money, things like that. Also, they are supporting to have new buildings in our universities and research centers, especially for new branches in chemistry, especially for the biomaterials, nanotechnology, and so on. Also, they supporting the interaction between the academy and the society, because all their point of view is going to the society. And actually, we are all working in research for society. So I think we will start our first step, inshallah, as I told you. We'll have at the last week of April 2024, our international workshop. We will invite the coordinator of the COMSTEC, Professor Iqbal Shidari, from Pakistan, and Dr. Hayat Sidney from Saudi Arabia, which is the manager, and she is actually, alhamdulillah, a close friend for me from Saudi Arabia. They will be our guests, and I hope many number of Islamic countries can participate in this event, also with the cooperation with their gathering, or we can say union, or a society of chemistry in their countries. And I think it will be a good chance, inshallah, to apply to be members, and after that the official steps to finalize these things will not be our business, it will be the business of the higher education ministers, and also such kind of, also with the, I think, foreign ministries. And I hope, inshallah, it will be a first step to have some support, and I think all of us needing this support for our research. Thanks so much.
Many thanks, madam, for your presenting Comstech.
Actually, this is the
memberships. Yeah.
If you can have some photocopy of it, it will be okay.
Okay, yeah, all right, yeah, thank you. You can also look up for Comstech online, so they have their own website, and you can actually have more information about that. So not go any further from here. We will go for lunch now for that, and I will resume the oral presentations this afternoon. There is room 312 upstairs. Please do look at the schedule in the booklet that you have in your handheld bag, and please be assigned straight to the rooms where you should be giving your oral presentation. So yeah, enjoy your lunch, and we hope to resume at around 2:30. Okay. Okay. Yes.